Okay, we're going to be looking at a few more probability games. So, when you're talking about rolling a pair of dice, sometimes it's easier to go back and say, instead of a pair of dice, what would it look like if I just had one dice? So, a dice has got sides. It's got one, two, three, four, five, six. So, right now they rolled it once and I got a one. So, what if I rolled it multiple times? And when you're actually doing something, that's called experimental probability as compared to theoretical probability. In theory, every one of these numbers are on that dice one time. So to roll a 5, you have a 1 out of 6 probability that's going to happen. 4 would be 1 out of 6. 3 would be 1 out of 6. But in reality, would that always come out to be perfectly true? And the answer to experimental probability would be no. But the more times you roll it, the greater that it comes out to be the theoretical. So I'm going to hit row, and then this case, I've got a 1 and a 3, but now I'm going to hit row automatically and just let it keep going and going. So all of these bars should be level in theory, and I've rolled it 47 times. But theory and experimental will not always match, but it comes closer and closer to each other if I continue this experiment and let it run on for a lot longer time. So you can kind of see that even though the bars kind of go up and down, if I let this run forever and ever, then pretty much the bars will pretty much be equal. Um, and that's the best you can do. If you say, what's the chance that something's going to happen? You normally have to go off the theoretical probability. Same thing of flipping a coin. You have a 50% chance of getting heads. But is it possible that you flip a coin 5 times and it all comes out to be tails? Yes, because you cannot predict what's actually going to happen. You can just kind of make a prediction, but it may not fit to that prediction exactly. So, one thing I would look at too is if you're going back and rolling what's called a fair die. You have different games at which the sides of the dice could be weighted, and that would make the dice not be fair. So you're having to guess the probability that a pair of dice will roll to a total that's less than 7, greater than 7, or equal to 7. So you've got to kind of understand what that sample space would look like. So going back to this game, I can change this to be 2 dice. And when I'm looking at what the 2 dice could be, I could roll a 3 and a 3. I could roll a 4 and a 6. 4 and a 5. So all of these are showing me all the different choices. Now, this goes back to sample space. If they ask you to write the sample space, they're asking you to give me every possible outcome that could happen when I roll a dice. So when I'm doing sample space, I'd want it to be organized. I could roll a 1 with a 1. I could still have the first dice be a 1 and the second one be a 2. So each one of these second dice I could be changing, and it could be anywhere from 1 to 6. Well, the next set of things that could happen is the first dice could have been a 2 all the way down, and the second dice could go 1, 2, 3, 4, 5, 6. So I'm not going to write them all down because it'd take me a while. Then the first dice could be a 3, and then this could go 1, 2, and then 3, 4, 5, 6. So if I listed all of these out to figure out the short way of how many would there be, well, you're looking at how many outcomes are on this very first dice. You can get 6 choices. You can roll a 1, 2, 3, 4, 5, 6. The second dice, you can roll a 1, 2, 3, 4, 5, 6. And according to the fundamental counting principle, when you multiply how many choices you have, that will tell you how many outcomes are there. So there are 36 outcomes. But what you're trying to do is trying to figure out, of those 36 outcomes, Are you going to get sums that are less than 7 or greater than 7? So what they mean by that is if I rolled a 1 and a 1, that gives me a sum of 2. If I roll a 2 and a 2, that gives me a sum of 4. A 3 and a 2 gives me a sum of 5. So you're trying to make a prediction of how many of these sums would be less than 7 or more than 7. So if I go back and I let this start, you're making a guess. Less than 7 or greater than 7. So let's say that I think it's less than 7, and I wasn't for sure how to get this game going. Evidently, I don't know how to play this one. Going back to this, let's roll it and let's let it keep rolling automatically. So remember, you can maybe come up with the theoretical probability by actually listing all 36 and figuring out how many of those would give you a sum greater than 7. And then you can then run the experiment and actually see if that comes out to be what you thought it would be. So according to this experiment, it looks like getting a sum exactly equal to 7 is greater than anything that could happen. So if I'm looking at, well, what dice could I roll that would give me a 7 perfectly? I could have rolled a 1 with a 6, which is different from rolling a 6 and a 1 because these are two different dice. This is the first dice, the second dice. First dice, second dice. I could have rolled a 2 with a 5 with a 2, a 3 with a 4, a 4 with the 3, and I think that's it. Because if I go to 5, I got 5 and 6, and you don't have a 7 and a 0 that you can roll. So you've got 1, 2, 3, 4, 5, 6. So you get a sum of 7 6 times out of that sample space, 36. So in theory, 1 out of every 6 times you roll these two dice, you should be able to get a sum of 7 perfectly. So if I had chosen that as in that game, then I would have won that game. So something you could have also done, I can go back, I can do 3 dice. Now if I got 3 dice going on, you got to think about what that would mean. You're rolling 3 at a time and then adding possibly the sums up. That sample space would take you a while to write out because there are 6 faces on this dice, 6 faces on this dice, 6 faces on this dice. So if you roll all of those, you would have 216 different options. Now, the largest sum you could get, 6 is the biggest number in all of these dice. So if you rolled a 6 and a 6 and another 6, that would have given you a sum of 18. You could have rolled a 1, a 5, and a 5, which would have given you a sum of 11 that they're recording right here. So let me clear this off a little bit. And rolling it again. So now 12 or 6, 6, and 3, that would have given you a sum of 15. So I'm going to let it roll automatically. We're going to see what sum appears more than any other sum because the combination of numbers, there's more of those that will get that to add up to. So according to this, it looks like it's going between 8 and 12. Now I've got 9. So if you keep letting this run, and to figure this out, you'd actually probably would have to go and look at all the different ways you could get a 9, all the different ways you can get an 8 and a 12, and then figure out which one of those ends up coming out the highest. To me, it seems like 9 must be the one that comes out to be the sum the most often. So that kind of gives you a rundown of the difference between theoretical and experimental.